Good afternoon, everyone. Welcome back. Today I will solve problem 25 of DeepML called single neuron with backpropagation. I think this is one of the most important problems on the website, especially because this can set the stage for you to work with more custom neural networks, especially if you want to do them with NumPy. With PyTorch, there's a lot of so-called shortcuts that you can do, although the official solution on the website is quite similar to what we're going to do with NumPy. But what I'm going to do here is I'm going to walk you through the step-by-step process. And although this is a very simple so-called exercise because it's just one neuron instead of a very dense neural network, the principles are the same, and you're going to keep working with this at all times. So I think this is an exercise worth doing, and I'm going to here solve it just with NumPy again because the PyTorch solution is quite similar, but if there's enough demand for that, then I may make a video on it as well. So in this problem, what we have to do is write a Python function that simulates a single neuron. It's going to have a sigmoid activation layer, and we also not only have to implement the forward step, we also have to implement the backpropagation, the backward step, which is where a lot of people get confused, and there's a lot of linear algebra happening underneath the hood, especially just trying to make sure that all of the dimensions of the elements that you're working with make sense with one another. So in this problem, we're given our input, which here it's called features, which is going to be our X or, our input matrix, as we will know it, labels. So this is going to be kind of a binary classification problem. And so what we're trying to do is we're trying to generate binary labels. That is, each element is 1 or 0. And here they're collapsed within a list that we're going to work with as a NumPy array. We're also given an initial weight. So we start with one guess or idea of what the weights could be. And then through backward propagation, we're going to try to find the optimal weights. Same for the bias. We're giving a learning rate, and we're also giving how many epochs we want to do this for. And again, if you're not very familiar with the whole principles here, I would suggest you to review at least what a neural network is supposed to do, what a single neuron is supposed to do, because as we can see here, I'm going to skim over the more technical details of it, because if not, this video would be very long. But so long as you know what every of the different ingredients that I told you about are, then you're good to go and we are able to solve the problem. So here, for example, it's telling us that after running the single neuron with backpropagation, we have to output what are the optimal weights, bias, and the mean squared error value. So we're going to, for each epoch, calculate the mean square error, store it into a list, and then return that as well. And this is great if you want to make sure, if you want to track whether your model's overfitting, if you also want to track whether, some of your hyperparameters are not working as you intended. This is a good way if you're working with this in production, or, if you're debugging a model, this is what you would like to take a look at. Okay, so all of that being said, how does this neuron work? And I think that this learning section that they have here for this problem is very straightforward. So I'm not going to start drawing as with other videos. I'm just going to go over it. So when you're working with a neural network, what you have to keep in mind is that there's mostly two big steps. The first one is the forward propagation, and that is given your weights and your bias, you generate a sequence of operations with your input. In this case, you multiply your weight matrix with your input, and then you add the bias. And the bias doesn't necessarily have to be a scalar. It could be, it could have other dimensions depending on your input, but for this problem, it's a scalar. So once we calculate this intermediate value, which we're going to call C, what we're going to do is we're going to activate that. So in order to map this from whatever the value of these multiplication of matrix and adding the bias is, we're going to map that to the labels, and we're going to do that by using the sigmoid function. And if you're not sure what the sigmoid function is, I think I have a video talking about that problem, so go take a look at that as well. So these are the steps of the forward pass. We just multiply matrices, and then we apply this sigmoid function. Then once we do that, we would like to see how good of a fit we have. So that is what we have, is the model, the prediction that a model is doing good enough? And how can we measure that it's good enough? Well, we have some ground truth labels, the Y vector, or what we know here in the input as the labels. And so we try to figure out how different our predicted values are from these labels. And the way that we do that for this particular problem is by using the mean square error. So basically, we just calculate the differences, square them, and then just take the average of that. Once we have that, so let's think about it for a moment. We would like the mean square error to be as small as possible. So once we iterate on each epoch, if our prediction, so if you had done an epoch before and your mean square error is going down, then that means that your model is better adjusted to the labels. Doesn't necessarily mean that your model is better, again, because it could be overfitting, but it could generally mean that you're taking a step in the right direction. So now that we have that, we would like to know, given this information of how our model performed, how can we update our models? How can we make sure that our weight and our bias is getting closer to what would be considered the optimal values? And the way we do that is the backpropagation. So remember that I said we would like the mean square error to be lower. How can we measure change in mathematics? We use the derivative. So you basically calculate the derivative with respect to the weight. So here we're not derivating with respect to the matrix, we're derivating with respect to each of the components of the weight matrix. That is why there's a subindex J, and we have this expression right here. And we also do the same here with the mean square error for the bias. And you can derivate these calculations in a relatively straightforward fashion. What's interesting here is that we have the derivative of the sigmoid function. So this is the sigmoid, symbolized by this delta, and by the sigma, sorry. And here we have its derivative. And so we would like to know what the derivative is. Again, there's another video where I talk about that. I'm going to talk about its exact expression once I go into the code, but it's a relatively straightforward one. And we have one for the weights and we have one for the biases. And then this is how you update the parameters. So for each components of the weights, you simply, and for the bias as well, you just subtract the learning rate times the derivative. And you're doing that because you want to move counter to the gradient. And again, I also have a video about gradient descent, so you can go take a look at that if this is a bit confusing. As I said, I'm going to skim over some of these components here, but the main idea is that if our mean square error were to be increasing, we would like it to decrease because there should be a minimum, right? So if we're going up, we want it to go corrected and go down, and the opposite. So we always want to try to reach the minimum of this function because it's a cost function. Okay, with all of that being said, let's translate this into code. And if you followed up until here and if you understood what the forward pass and the backward pass do, then I think it's relatively straightforward to code this into NumPy. The biggest difficulty, at least it was for me when I was starting out, was to figure out what the dimensions of each of the elements were. And so we're going to work on this. I have my code on my other screen because I tried to record this without having the code written up, and it just took me forever, and sometimes I made some mistakes, so I want to give you a better experience. So, okay, let's start out by making sure that we have everything that we need here. So here we're supposed to return updated weights, updated bias, and mean square error values. I'm just going to, because I'm a bit lazy and I don't want to type updated weights and updated bias all the time in my code, I'm just going to change the names of this to WMB. And so let's define what we need to have before we start iterating in the first epoch. And so first, let's initialize the mean square error values as an empty list, because there we're going to store all of the values of the loss function. Then what I'm going to do is I'm going to change some of the names here, because as I said, I don't really like to type a lot here. So for example, features, I'm going to rename as X, and I'm going to make sure that this is an array. It's supposed to pass an array, but there could be some pathological case where somebody passes a list, for example, and you won't have access to all of the NumPy stuff you want. So I just do this as a good practice. So instead of using features, I'm going to use X. Instead of using labels, I'm going to use Y. Instead of updated underscore weights or initial underscore weights, I'm just going to do W, and I'm going to put this as array. And finally, for the bias, the same thing. Well, the bias is a scalar, and so this thing doesn't really matter, but I'm just doing it for consistency's sake. Wait, now, one good thing that we should do, well, before that, let me just define n, which is going to be the number of observations. That's going to be the length of x. Okay, one very important thing to do, it's not mandatory, but I think it's great so we can keep track of how to work with this thing, is to make sure that we know the dimensions of the elements that we're working with. So for example, here, X is going to have n observations, so n rows, and each row has different features. So in this example, for example, there's two different features. So there's 3 observations, 2 features. And so we could say that X has a dimension of n rows and f columns. I'm just using f to denote the number of features. Y, on the other hand, so this is a different label for each of the observations, so it should just have a dimension of n. W, which is the weights, well, this should have a dimension of f. So we have one different weight for each of the different features that we're working with. And the bias is just a scalar, so I'm just going to put one here. You would also, right now it's stat, but as we're going to see later, maybe you could argue that this is n. This everybody has the same bias, so I'm just saying that it's a scalar here. But in theory, we're going to operate with it as if it were a vector. And if you're not following that, don't really worry. It's going to make sense in a bit. Okay, so now we have defined everything we want. Now let's start working with each of the different steps of our iteration. So we're going to do one iteration for each epoch. So for each epoch, what are we going to do? First thing is do the forward pass. Second thing is calculate the MSE. This is just the steps from the learn section. And then finally, we're going to calculate the backward pass. Okay, now that we know that, let's get to work. So we saw here in this part that when we're calculating C, the score, we have to multiply the weight and we have to multiply the features and the weight matrix. So how are we going to do that? Well, we have to make sure that the dimensions match. So X is n rows, f columns. W is f columns, and here, you could say it's just one. F rows, excuse me, and just one in terms of columns. So the way that they can be combined together is by combining wherever they have the same dimension. So here they have f, here they have f here. So we're going to do a matrix multiplication that's going to require the step x at w. So take a look at that. This operation is going to be n comma 1 because this comes from linear algebra when the number of columns from the first matrix matches the numbers of rows of the second matrix. They kind of like combine together. And so the output is going to have the same number of rows as the first input and the same number of columns as the second input. So that's how we know that this is a valid operation. And I'm taking a lot of time explaining this step because this is where I failed multiple times when I was trying to do this for the first time because I wasn't sure what was supposed to match with. I was very messy. I didn't keep track of these functions, and I don't want that to happen to you. So that's why I'm being very cautious with that. Then, as here, we're adding b. Now, you may be a bit confused because this is going to be a vector and b is a scalar. But in NumPy, when you're doing this kind of addition, this just gets broadcasted. So this b is being treated as if it were a vector where every element of the vector has the same value. So that's what I was alluding to at the beginning of this part. Okay, so all of that is going to be the first step of the forward pass, and we're going to call that C. And then in the next step of the forward pass, what we're going to do is that we're going to get our predictions, and I'm going to call this spreads. And the way we get those predictions is by applying the sigmoid function to what we just computed, which is C. Now, you may be saying, hey, we haven't defined the sigmoid function, and you're correct. Let's go do that right now. Now, there's a more efficient way of defining the sigmoid function. I'm just going to go with this one in the example because I'm feeling a bit lazy, and also it doesn't really matter for the test cases that we have on the website right now. But in practice, you could think about different ways of writing the sigmoid function. Anyway, we have written this auxiliary function called sigmoid, and we're calculating it, using it to calculate the predictions. So now we have the forward pass done. That's great. One thing that's kind of convenient though is, I'm just going to do that in the mean square error thing. I was going to say one thing that's convenient is to just store the difference between the predictions and y into a variable that we're going to call errors. And again, what is this? Well, the predictions are the same as C, so this is going to be n1, and y is n1 as well, so this is going to be n1. Okay, fantastic. Now that we have that, we can calculate the mean square error, which is this thing right here. There's multiple ways of doing it. I feel more comfortable just thinking about it as a mean and then just applying the function np square, which is basically just going to square every element within a vector to the vector name errors. So that is how we're going to get this exact value right here. Now that we have the value, one of the first asks in the question is to store them into a list. So I'm going to add this to the list we defined called MSE values. And I'm going to add the error that we just got, sorry, the MSE that we just got rounded to 4 decimal points. And I noticed from the test cases that this is mandatory for the MSE, but it's not necessarily mandatory for the WMB. But you could do it for them as well if you want. Okay, so we have done 2 of the 3 steps within this question. Now comes the most interesting part, in my opinion, which is the backward pass, which is this whole thing right now that I talked about. So how are we going to do this first? First of all, let's keep in mind that the derivative of the sigmoid function has a known expression. And again, I have another video talking about it, but for example, if the value of the sigmoid, let's just call it s, then the derivative of sigmoid is s times 1 minus s. And you can very easily derive this with math. For now, just take it as gospel, and we're going to work with this expression because we have the derivative of the sigmoid appearing here. Okay, that's great. Let's start working with that. What we need to do to perform the backwards pass is to find both of these expressions right here, both of these derivatives. In the both of them, we have almost the same parameter, so to speak. So it's almost the same value. So we have these 2 over n, which is the number of observations of the sum of this thing, which is the difference between our prediction and the labels, which we call errors right here, times the derivative of the sigmoid. So let's first store that into a variable. So first, I'm going to define sigma derivative, sigma dir, as the sigmoid function, which we call the result of the sigmoid of our forward pass, which we call prets, which is given by this expression right here. And then what we're going to do is we're going to store this parameter in memory, this variable. And I'm going to call it, I think in the solution you call it delta. So I'm going to call this thing delta right here. So I'm going to call this delta, and it's going to be 2 over n times errors times sigma derivative. Now, what are these things? Well, we're not doing matrix multiplication here. When you have the asterisk in NumPy, you're doing an element operation because pret is n1. This one is also n1, so we get n1 here. And same thing here. So errors is n1, sigma derivative is n1, and we're doing an asterisk. So it's not a matrix multiplication. So we have this n comma 1. This is just so you get used to keeping track of the dimensions of the variables. If not, it's going to be a headache. Okay, now that we have all of that, let's write our derivative. So first of all, I'm going to start with the derivative of the bias. So this one's the most simple. So here we have, this is n comma 1. And from this expression right here that we have in the learn section, we know that this should be a scalar. So the only thing that's missing here is to sum all of the elements together. So what we're going to do is we're going to do delta. This is the best way of doing it, delta.sum. And so we're going to have a scalar right here. So if you're a bit confused on what just happened, this delta variable right here corresponds to all of this thing without the sum. So it's not applying the sum. It's just having this thing right here. So we have that, and we have that there's the derivative of the bias. Now, for the derivative of the weight, we have to do something similar, but let's think for a moment. What's missing here is our beautiful element x, right? And what dimension do we want dw to have? So dw is going to tell us how each of the different weight values for each of the different features change. What are the dimensions of the weight matrix? It's F1. So because we're going to add them, we're going to add the weight matrix with this derivative. We would like this derivative to have the same dimensions. So we would like this thing to be F1. Now, how do we get that? Well, we have here that delta is N1, and we know that we have to use the X somehow. We cannot just go ahead and multiply. We cannot do this, for example. We cannot go and say X at delta because the dimensions are not going to match. The X is NF and delta is N1. So the dimensions do not match. Remember, the columns should match the rows. So what we're going to do here is do something a little bit tricky. And so we're going to transpose the X matrix. Because once we transpose it, we flip the rows and the columns. So we're going to have this being Fn. And in that way, they have compatible dimensions. And so we can do this operation. So Fn matrix multiplication with N1 is going to be F1. And so that's going to match. And we're going to have what we wanted, which is that the weight, the derivative of the weight is going to have the same dimension as the weight matrix, which is how it should be because they should have the same dimensions so you can track the variation of the weight matrix on each of the different dimensions that matter. So all that, that's the trickiest part. That's why I've been very persistent in trying to keep track of all of the different dimensions throughout this process, because if we didn't, then this part can be a little bit tricky. You may be confused. You may not be entirely sure what's going on. This can give you a good idea of why. Okay, so we have all of that. Now let's just finish this up by saying that W at the end of this iteration, W is going to be equal to W, the previous W, minus the learning rate times the derivative of the weight, and the same for the bias. And with that, we pretty much have solved the problem, because what we want to have as our output is the weight and the bias at the last iteration, at the end of the epoch. So once we go out of this for loop, we're going to have the last values. And we already took care of the MSE values. So with that being said, let's run the code to make sure that everything worked. And we should get a pass in the test cases. And we just got an error. Oh, local variable X reference before assignment. Oh, okay. I had a very silly error. If you can see, I defined n, which was the number of elements in X, before I called this thing X, because remember, as the input is called features, but now I just moved it after I defined X, and that should be it. Okay, fantastic. So that passes all the test results. Hopefully this video helped, and I'll try to get back into making more videos now that I got a bit more time. So thank you for watching. I hope to see you on the next one.